Good evening, guys. Hope you're doing well. I'm glad you're back with me. This is lecture number 4 for Chem 110. So this is moles and percent composition. I know that some of you, this is a slightly different lecture number for you based on the difference in the schedule for summer full versus the fast forward. So this might be a different lecture number for you, but it's still moles and percent composition. That's how it's presented in the schedule. All right, let's go ahead and get started. I will share my screen so that you guys can see what I'm talking about. So like I said, moles and percent composition. Awesome. So what are we going to talk about today? We'll talk about Avogadro's number, the molar mass, the molecular mass, calculations using moles, mass, and number of atoms, percent composition, the determination of an empirical formula, and the determination of a molecular formula. Right? So those are the things that we're going to talk about. But we're going to do what I always like to do and start with some review questions based on the lectures that have come before this. So we're going to ask you a whole bunch of questions based on what you should already be assimilating at this point. So what are my questions? Well, I have a bunch of them. So I'm just going to read through them first, and then I'm going to walk you through what I do and how I do it. What's the full electron configuration of arsenic, As? What's the formula of dinitrogen pentoxide? What's the abbreviated electron configuration of silicon, Si? What's the name of Fe2CO3? What is the formula of rubidium phosphate? What is the name of NH3? Pick an atom, write its symbol, atomic weight, and its common ions. Pick one ion and write its electron configuration. Electron configuration of argon in both the full form, the noble gas notation, and the drawing out of the orbitals and electrons. How many significant figures are in the following numbers? And then consider a solid with a mass of 19.462 grams and dimensions of 3.14 centimeters by 1.462825 centimeters and 2.7262 centimeters. What is the density of the material? So those are the things that we're going to be talking about. In order to talk about that, I'm going to pull up my paper and I'm going to pull up my periodic table so that we can talk about some of these things. Eventually I'll need my calculator and I'll pull that too. So what's the full electron configuration for arsenic? Arsenic, which is As. Now if I look for As on my periodic table, and I actually don't see it right here, so I'm going to slide over a little bit. Arsenic is number 33. I know that it's after argon. It's in the 4th period, so we're going to be talking about quantum level 4. So if it's in quantum level 4, I don't want the full electron configuration. I know it's 1s2, 2s2, 2p6, 3s2, 3p6. That gets me up to the 4th row. Now, since I'm in the 4th row, I'm going to have 4s2. Then I'm all the way over in this p section. So I know I've got 3d10. 3d10. Because remember, this d group here is n-1, so that's 3d10. And then we're in the 4p's again. So I'm in 4p, and I have 1, 2, 3 electrons there. So in this p block, there's 1, 2, 3 electrons there. So that's 4p3. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p3. Okay. Now, sometimes when you look at this, some people will show you that this is 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4p3. The order in which it appears really isn't that important. I do it in the order it fills in the periodic table because that makes a lot more sense to me. But it really doesn't matter in which way you've learned to do it if you've done that before. So what's the formula of dinitrogen pentoxide? Well, nitrogen is N. There are 2 of them. Oxygen, or oxide, is oxygen. Pent means 5, so it's N2O5. Okay. What is the abbreviated electron configuration of silicon, Si? Now, that's over here somewhere. Silicon is number 14. So his abbreviated electron configuration is going to be neon, which is number 10. So I have a neon core. Then I'm in the next row, which is 3s2, and then 3p2. So remember, we did our 1s2, 2s2, 2p6. That's our neon core. Then we have 3s2, 3p2, 1 and 2. So that's my abbreviated one for silicon. What's the name of Fe2CO3? Fe2CO3. Well, I know that this is a cross multiplication. So I know that this is an Fe3+, and I know that it's CO3 2-. I know that that's going to be iron 3, because again, I didn't know what the charge was, so I have to indicate what the charge is. And then CO3 2- is carbonate. I happen to know that that should be on that table for you so that you can find it in the polyatomic ions. Okay, so that's iron 3 carbonate. Awesome. What's the formula of rubidium phosphate? Well, rubidium is number 37. It's this guy right over here. Rubidium is that guy, so he's Rb. Phosphate is PO4. Charge on that is 3-. So this is 3-. Rubidium, being where he is going to be a +1. So I'm going to need Rb3PO4. So that's the formula for that. Awesome possum. What's the name of NH3? NH3 is ammonia. Okay, so that's, we can also call it nitrogen trihydride. Nitrogen trihydride will also work. Now pick an atom, write its symbol, atomic weight, common ions, pick one ion and write its electron configuration. Common ions, okay, fine. So let's talk about oxygen, because oxygen's a fairly common one. So oxygen's over here. He's in the second row. He's number 8. So if we're talking about oxygen, its symbol is O. Its atomic weight is listed as 16. And it's 16 AMU, which we'll talk about in a few minutes, or grams per mole. Where am I? Oh, yeah. And it's common ions. Well, I know that O can be 2-, but I also know that occasionally O is just minus. So we see that occasionally. Pick one ion and write its electron configuration. I'm going to choose the most common, the O2-. So let's talk about what it would be just for oxygen. So if I use that helium core, then it's going to be 2s2 and then 2p4 to get to the number 8. So there's p 1, 2, 3, 4. But it's a 2-, so it's added 2 electrons, which means it's actually 2p6. Okay? If I wanted to write the whole thing, it'd be 1s2, 2s2, 2p6. Okay? And then they want us to draw out the orbitals. So I'm going to do this in this format. 1s, 2s, 2p. I know that the 1s is full, the 2s is full, and my 2p is also full. So that's what I have for that particular ion. Okay? That's everything for that. Woohoo! I did it. Go me. What's the electron configuration of argon? So Ar, argon. In its full form, the noble gas notation, and the drawing out of the orbitals and electrons. So argon is number 18. It's the one right here. So he's in the 3rd period. That means he's going to be a noble gas configuration, either Ne3s2 3p6, or I could just list him as argon. That is a noble gas configuration, so that works as well. the full thing is going to be 1s2, 2s2, 2p6, 3s2, 3p6, because the neon is the 1s2, 2s2, 2p6. All right, so that's that. That's the full form noble gas notation, and then drawing out of the orbitals and electrons. So 1s, 2s, 2p, 3s, and then 3p. And of course, 1s2, 2s2, 2p, 2, 4, 6, 3s2, and then it's 3p6. So this is full as well. Okay? Yahoo! Yay! Now, how many sig figs are in the following numbers? I have 2.00000005. So I have all of those numbers are going to be significant because all the zeros are in between non-zero numbers. So I have 1, 2, 3, 4, 5, 6, 7, 8 sig figs in that first number there. 205 and then a bunch of zeros. So all the zeros at the end are simply placeholders. I could put this in scientific notation and get rid of all those placeholders at the end. So that's 3 sig figs. And this 205 with all of those zeros out there, those are not just placeholders. They've been put there for an explicit reason. So it's 3 sig figs for the 205. 4, 5, 6, 7, wait, hold on. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I got 12. Hopefully I can count. Okay. Sometimes it's hard for me to see that, and so it's difficult for me to tell. That's really what it is. But that's what we're talking about. So again, placeholders with no decimal place, that's not going to be significant. The zeros after the 205, all of those are written there for a reason. Those are significant. And in the first case, all of them are significant because they're between two non-zero numbers. Now I want to consider a solid. It has a mass of 19.462 grams, and it has dimensions of 3.14 centimeters, 1.462825 centimeters, and 2.7262 centimeters. Now, density, which is what I've been asked for, density is grams per mole, all right? So if that's what I'm talking about for density, then I need to take this mass, or not grams per mole, I apologize, it's grams per volume. And volume can be centimeters cubed. So I'm going to go ahead and report it in grams per centimeters cubed. So that means that I'm then going to take the 19.462 grams. I'm then going to divide that by 314 centimeters, 1.462825 centimeters, and 2.7262 centimeters. And that's the math that I'm going to do for that. Let's pull up our calculators. Woohoo! Oh, sorry, I was playing with something. 19.462, divide that by 3.14, divide that by 1.462825, and then divide that by 2.7262. And that gives me 1.55 and a whole bunch of digits out there. So now the question becomes, how many sig figs should I be reporting for this answer? Well, let's talk about that. I have 5 sig figs in the 19.462, 3 sig figs in the 3.14, 1, 2, 3, 4, 5, 6, 7 sig figs in the 1.462825, and then 1, 2, 3, 4, 5 in the 2.762 centimeters. The lowest of those is the 3 sig figs, so I'm only going to report this as 3 sig figs, and it gives me 1.55 grams per centimeter cubed. Okay, and that's everything that we wanted to review. Whoa, that was a lot, but it wasn't as bad as it could have been. Okay, so that's everything that we talked about there. Review is good. Awesome. Let's keep going. Questions, comments, problems? If you have them, let me know. Keep me apprised of anything that you're running into that's an issue. And let's continue on from here. So, who is this guy Avogadro? Well, just like I can say that there's a dozen of anything is 12. Dozen is 12. We have this number called Avogadro's number that was discovered by this guy Avogadro. Okay? Doesn't really matter who he is, but he has a number that is 6.0221413 times 10 to the 23rd. We generally round that to 6.022 times 10 to the 23rd. That is the number of particles contained in 1 mole. And it doesn't matter what kind of mole we're talking about. They're all defined as that number of atoms or molecules. So 1 mole contains that many particles. All right? Moles are much easier to work with. We can talk about a lot more things in terms of moles. The molar mass is defined as the mass of 1 mole of either an atom or a molecule. So if I have 1 mole of those things, then I have the mass of that mole as the molecular mass. Okay? So that's Avogadro. Ooh, awesome. Let's talk about molar mass again. The mass of 1 mole of a substance is the same as the atomic mass, provided you use the atomic masses on the periodic table. So what is technically listed on the periodic table? Well, let me show you a periodic table just so we can have this discussion again. So on the periodic table, you'll see this number. This is technically an atomic mass. So that's 16 is actually 16 atomic mass units. It represents the mass of 1 oxygen atom. Okay, so it's an atomic mass unit. But if I'm talking about molar masses, I know that if I have 1 mole of this material, then I also have 16 grams of that material. So I can list it as AMU if I'm talking about a single particle, or I can list it as 16 grams if I'm talking about a mole. So that's what's going on there. All right. That means, and that takes into account the normal distribution of the isotopes, all that stuff that we talked about before. That means that if I know the mass of a sample of any element, I can know the number of moles of that element that I have. And that will tell me how many particles are present. Oh, Lord, here we go. So I have 13.56 grams of lead. I want to know what's the molar mass of lead, how many moles of lead do I have, and how many lead atoms. All right. 13.56 grams of lead, which is Pb. What is the molar mass of Pb? How many moles? And how many particles? In this case, lead atoms. All right, I need a periodic table if I want to figure this out. So let me find a periodic table again. Pull up my periodic table. I'll maximize this. And all right, I want to find lead. Lead is right here. So he is number 82. His mass is 207.2. So 207.2 AMU or 207.2 grams per mole. Molar mass is going to be the 207.2 grams per mole. Awesome, awesome. Now, how many moles of lead do I have? So I have 13.56 grams, right? So that's less than 1 mole, because 1 mole would be 207.2 grams. So I need to convert this number of grams into a number of moles. I do that by taking the mass of lead that I have and dividing it by the mass per mole. So it's grams per mole. The grams are going to cancel and leave me with an answer in moles. So I'm going to take my 13.56. Hey, come back here. 13.56 and divide that by 207.2, and that's going to give me an answer of 0.065444 blah, blah, blah. 4 sig figs, because I have 13.56, so it's 4 sig figs, 0.06544 moles. That's my answer. Whoa, awesome. How many lead atoms Well, I use Avogadro's number to get from moles to number of atoms, right? I know that there's 6.022 times 10 to the 23rd atoms per mole. So if I have 13.56 grams and I convert that to moles using the molecular weight, I cancel the grams. I can then multiply by 6.022 times 10 to the 23rd atoms per mole. And that will give me the number of atoms. Now, oh, geez, sorry, you couldn't see that. That is this here. Now, why have I set this up like this as opposed to taking this number that I reported here? Well, if I take the number that I reported there, I rounded that number. And so if I use that to do this next calculation, I'm going to end up with what we call rounding errors because I did the rounding. So Alex isn't going to like that if you do it. So you want to take this conversion the way that you've done it here with this whole set of numbers that it spit out and multiply that by 6.022 second E23. And that will give you the answer that you're looking for. Which again, if I want to report this as 4 sig figs, which I should because of the 13.56, then that's going to be 3.941 times 10 to the 22nd atoms. Okay, so that's what we're talking about there. That's how many of them I have. So now I've calculated the molar mass. I looked that up. How many moles of lead that I had using the molar mass to divide the mass that I had to give me number of moles. And then I've used that number of moles to calculate the number of particles using Avogadro's number. Okay, so those are the calculations that I've been through with that. Now, let's go back to our slides and keep going. Maybe. Molecular mass. So aka molecular weight, you may hear either term, is the mass of 1 AMU of one molecule. Okay, so it's also the mass in grams of 1 mole. So it's the sum of the atomic masses for the components in the molecule. So we want to talk about the mass of H2O. We need the mass of hydrogen times 2. So 2 times 1.01 grams per mole, plus the mass of the oxygen, which is 16 grams per mole. That gives me a total of 18.02 grams per mole. If I want to talk about NaCl, I need the mass for the Na, which is 22.99 grams per mole, plus the mass of the Cl, which is 35.45 grams per mole, which gives me 58.44. And again, those numbers are coming from a periodic table. And so if I go back to my periodic table, I can see that Na is 22.99. I can see that Cl is 35.45. I can see that hydrogen is 1.008, which we often report as 1.01, and oxygen is 16. So that's where those numbers are coming from that I'm using to do those calculations. I've pulled them directly off the table and I'm adding them together to get them a total mass. All right. NH42CO, this means that I have 4 times hydrogen, so the 1.01 grams per mole, plus 2 times the nitrogen, which is 14 grams per mole, plus the mass of carbon, which is 12.01 grams per mole, plus the mass of the oxygen, which is 16 grams per mole, which gives me a total of 60.06 grams per mole. Right, so that's how I would calculate the mass of a molecule, is to count for everything that's in it and the correct number of them that exist in that molecule. All right, awesome possum. Let's keep moving. Now, can I do calculations with moles, mass, and number of atoms? Actually, yes, I can. I showed you one a couple of minutes ago. So if I know the mass of a substance that I have, I can calculate the number of moles that I have. So we consider oxygen, O2. It has a molar mass of 31.9988 grams per mole. How many moles of O2 do you have if a sample is 267.84 grams? So I take that mass, 267.84 grams of O2, and I multiply that by 1 mole of O2 being 31.9988 grams. So I'm actually dividing by the molecular weight. And that gives me 8.3703 moles of O2. It's 5 sig figs because the mass of O2 was listed as 5 sig figs. Okay? All right. How many particles of O2 are in that sample? Well, for this, we use the answer before I round it, just like we talked about before. Otherwise, you'll run into rounding errors that might make Alex tell you that the answer is wrong. So 8.370313887 moles of O2 times 6.022 times 10 to the 23rd molecules of O2 per mole of O2 is 5.0406 times 10 to the 24th molecules of O2. Since the mass of oxygen is rounded to 5 sig figs, the number of sig figs you should have on your answer is 5. So if I know the number of moles that I have, I can calculate the number of atoms. If I know the number of atoms, I can calculate the number of moles. If I have the number of moles, I can calculate the number of grams. If I have the number of grams, I can calculate the number of moles. So now I can go all kinds of different places with a mass, a molecular weight, and the number of particles that are in a mole. So now I've gotten all of these things that are in here. We're going to continue building on this, other things that we can calculate as the semester goes on. But that's where we are right now. Okay? Questions, comments, problems on that? If you have them, please let me know. Again, email, phone, talk to me in person, tell me which lecture we're talking about, what your question was, and I probably will be able to help. All right. The next thing we're going to talk about is percent composition. All right. Percent composition is the percent by mass of each element in a compound. So the percent composition of an element is the number of moles of that element times the molar mass of that element divided by the molar mass of the compound times 100. So what is the percent composition of carbon in glucose, C6H12O6? Well, let's talk about that for a second. So C6H12O6, and I want to know what the contribution is from the carbon. So let's take a look at the paper that I've been writing on. C6H12O6. I want to know the thing from carbon. So I'm going to have the number of carbons times the molar mass divided by the mass of the compound times 100. That's what I'm going to be looking for. All right. Well, if I want to do that, then I need to figure out what the molar mass of this compound is. So I have 6 times the mass of carbon. Carbon's over here. He's 12.01. So I'm going to do 6 times 12.01 plus 12 times 1.01. Well, 1.0008. And that's grams per mole. And it's 6 moles and 12 moles. And I'll show you this mess that I'm writing here in just a second. Plus 6 times, and it's 6 moles, times the mass of oxygen, which is 16.00 grams per mole. And again, I said I'd show you that mess, and this is that mess. So 6 moles times 12.01 grams per mole plus 12 moles times 1.0008 grams per mole plus 6 moles times 16.0 grams per mole. If I add all of that happy stuff together, which I can do on my calculator, I have 6 times 12.01 plus 12 times 1.000, 3 zeros, 8 plus 6 times 16, and that gives me this answer, 180.696. Now, I don't consider the 6, the 12, and the 6 when I look at my sig figs. Those are considered infinitely known. So they're not what limits my sig figs. So I have 12.01, which is 4 sig figs, 1.0008, which is 5, and 16.0, which is 4. So I'm going to report my answer in 4 sig figs, which gives me 180.1 grams per mole for that particular compound. Now, if I want to know the percent composition of carbon, so percent carbon is going to be equal to the number of carbons in this. So there are 6 carbons. So 6 molar carbons times 12.01 grams per mole. And then I'm going to divide that by 180 grams per mole. and then I'm going to multiply that by 100. So that's the calculation that I'm doing there. 6 times 12.01 divided by the 180.0696. And of course, technically, I'm 1 mole of this is this. So this gives me an answer that's in grams over grams, which is unitless. Awesome. And that gives me that fraction, which I then multiply times 100. And that gives me an answer of 40.02%. 40.02%. And again, it's 4 sig figs because I have 4 sig figs in my 12.01. So that's where I get the 4 sig figs for my answer. So it's 40.02% carbon. That's what we're talking about for that. Percent composition of carbon and glucose. Now I could do the percent composition of the hydrogen by multiplying the mass of the hydrogen times 12, dividing that in the same way, and calculating a percentage. We can do it for everything that's in there, but I wasn't asked for that, so I'm not going to do it here. Now, the next question that I have from this happy thing is, what is the composition of each element? Is ZN3PO4 2? Awesome. Well, let's look at our paper again. Paper, calculator, periodic table. And my paper says ZN3PO4. So I need to know the mass of ZN. I need to know the mass of P. I need to know the mass of O. The ZN, I'm going to have 3 times whatever I have there. I have 2 phosphorus, and I have 8 oxygen. So I'm going to have those components. And if I look, where the heck is he at? I can never remember. Zinc. I love it when I lose stuff. Oxygen is over here. He's 16. Phosphorus is right here, 30.97. Again, these are all moles. This is grams per mole, which gives me an answer in grams. And ZN, where have I lost you, ZN? Love it when I can't find stuff. So interesting. Ah, zinc, ZN, right there, 65.38. So 65.38 grams per mole. Now, if I do all that happy math, and I'm not going to calculate each one individually, although I could, I'm going to look at this and I'm going to say 3 times 65.38 plus 2 times 30.97 plus 8 times 16. That total is 386.08. Now, how many sig figs am I talking about? Typically 4, so 386.1 grams. That's my total mass for 1 mole of this happy compound. All right, but I'm going to leave that as grams. Now, if I want to know each component, if I want to do the percent zinc, then that's going to be equal to the number of zincs that I have, 3 moles, times the molecular weight of that, which is 65.38 grams per mole. And I'm going to divide that by 386.1 grams per mole, and then multiply that by 100 to get that percentage. So I'm going to take 3 times 65.38 divided by a second answer. And that's that. And I need to multiply that by 100 because I forgot to. So that's 50.80% zinc. If I want to go percent P, that's going to be 2 moles times the 30.97 grams per mole over the 386.1 grams per mole times 100. And that's going to be, dun, dun, dun. Oh, I didn't store that. Give me a second. I need to do this calculation again. So 3 times the 65.38 plus 2 times the 30.97 plus 8 times 16.00. And I'm going to store that in alpha A. All right, so now I've stored that molecular weight as it was calculated with all the digits that were there. Now I'm going to do 2 times the 30.97 divided by that answer, which again, I had just calculated so I can use it there, and then multiply that by 100. And that gives me 16.04% for the phosphorus. And then if I do the oxygen, same kind of thing, 8 moles times 16.0 grams per mole over 386.1 grams per mole times 100, and that's equal to da-da-da-da. Now let's go back in here, and we have 8 times 16. I'm going to divide that by, so I can recall alpha A. And then I'm going to multiply the whole thing by 100. And that's going to give me 33.15%. Now, if I do a gut check, 33.15 plus 16.04 plus 50.80, that's 99.99%. So I have within rounding errors, I have accounted for everything that I needed to account for. Right, so that's the percentage of each component when we're talking about what's in that. Oh, and here's all that happy math that goes with that. I'm so sorry. So percent zinc is 3 times 65.38 divided by the total times 100. That's 50.80. Percent phosphorus 2 times 30.97 divided by the 386.1, which should actually be the 0.08 times 100 is 16.04. Percent oxygen, 8 times 16 divided by 386.1 times 100 is 33.15. And I added them all together, and what I got was 99.99% within statistical rounding errors. That is my correct answer. Okay, awesome. Now, let's see what else this slide says. It says we can use the same process in reverse to determine the empirical formula of a compound. So if a mass percent of S is 40.05 and for O is 59.95, what's the empirical formula of the compound? So I'm going to write that down. S is 40.05%. O is 59.95%. And then it says I have the mass percent. I convert that to grams and divide by the molar mass. That gives me the moles of each element. I divide by the smallest number of moles, which gives me the ratio, and then I change that to integral. Right, that's all gobbledygook. What the heck does that mean? Well, let's see. So, paper, I said S is 40.05, O is 59.95. I'm going to assume that we're talking about 100 grams. And so I have 40.05 grams of sulfur. I have 59.95 grams of oxygen. I'm going to take each of those masses and convert them to moles by dividing by the molecular weight. So the molecular weight of sulfur, these over here, is 32.07. And oxygen, again, is 16.00 grams per mole. And now let me show you my paper again. So I wrote those right there. So now I'm going to divide the 40.05 by the 32.07 grams per mole of S. Grams cancel. That leaves me with moles of S. I will calculate that in just a minute. I'm going to set up the other calculation, 59.95 grams of oxygen. 1 mole of oxygen is 16.00 grams. 1 mole of O. Grams cancel. That leaves me with an answer in moles of O. Now I'm going to pull up my calculator again, and we're going to do some garbage with this and calculate some happy math. So 40.05 is going to be divided by 32.07, and that's going to give me 1.249 mole of S. And I'm going to leave that number as it is, okay? So I'm just going to leave it there. It's going to sit there for a couple of minutes. And I'm actually going to store that as alpha B because I'm probably going to want to use it again, okay? So that's that number there. Now I'm going to do the other calculation, 59.95 divided by 16, and that gives me 3.74. 3.747 mole of O. Now again, I may need this number, so I'm going to store this as alpha C. Now what it says is that I need to write this as a ratio, right? So I have S 1.249 and O 3.747 because I know I need subscripts that go with each of these things. Now those aren't even numbers, so I'm not going to be able to work with the numbers as they exist. I'm going to have to divide by the lowest number, which is what it said. So I'm then going to have S1 and O. If I divide 3.7 that divided by my second recall alpha B, that's 3. So that's SO3. Okay, that's how we do that. That's how I find the empirical formula from the information that I was given. All right. So we're looking for the smallest whole number ratio of those things. That gives me my empirical formula. I have now successfully calculated an empirical formula and the percent composition of each of these things in terms of that I was asked for. Go. Awesome. I just did stuff. Let's see if we can do more stuff. Percent composition examples. What is the percent composition of Mg Cl2? I'll do a percent composition for H2SO4. I want to know what the empirical formula for the molecule that has 40% C, 6.67% H, and 53.33% O, and an empirical formula for a molecule that has 31.42 S, 31.35 O, and 37.23 F. So let's start at the beginning and talk about what is the percent composition of MgCl2. So I want my piece of paper. I want to know MgCl2, what's the percent composition of MgCl2? Well, in order to do that, I need a couple of things. I need to know what the mass of Mg is. I need to know what this mass of Cl is. I need 2 times that mass for Cl. And I pull up my periodic table to do that. I have 1 mole of Mg in this. Mg is 24.31. And this is mole, 6 grams per mole. And my Cl is 35.45 grams per mole. I can calculate all of that happiness so I can get an answer for the total. So 1 times 24.31 plus 2 times 35.45. Total mass is 95.21. And I'm just going to leave it as the number that it spits out so that I don't have to worry about the rounding part because I know I'm going to do more with it. And that's in grams. If I want to go percent Mg, that's going to be 1 mole of Mg times 24.31 grams per mole divided by 95.21 grams times 100. So 1 times 35.45 divided by 95.21, and I multiply by 100 to get a percent. That gives me 37.23% Mg. I can do percent Cl, and I have 2 times 35.45 mole, grams per mole, divided by the 95.21 grams times 100. So 2 times 35.45 divided by 95.21 times 100 is 74%. And if I add those two together, 37.3 plus 74.47, that is not right. I do wrong. So Mg, let me check my mass. Mg is 24.31. This is 35.45. 1 times 24.31 plus 2 times 35.45. 1 times 35.4, let me go back up. 1 times 24.31 plus 2 times 35.45 should be 95.21. Okay, 24.31 plus 24.31 plus 2 times 35.45 gives me 95.21. So if I take 24.31, I divide that by 95.21, and I multiply that by 100, that's 25. Oh, my calculator exploded, which does happen from time to time. Now, see, this is part of why I do that test, because if it doesn't add to be 100%, something's screwed up. So 25.53% Mg. If I add 25.53 plus 74.46, that gives me 99.99 again, and that within error is perfectly fine. All right. Phew, calculator exploded and we still got there. Yay! What's my next question? What is the percent composition of H2SO4? H2SO4. Well, let's go back. Yes, and I want this. So H2, so I'm going to go mass of 8, which is 1.008 grams per mole. The mass of the sulfur is 32.07 grams per mole. And the mass of the oxygen is 16 grams per mole. So I can put that away for a while. So that I've written all of that down. I have 2 hydrogens times 2 mole. This is sulfur times 1 mole. And oxygen times 4 mole. That will give me a sum that I can work with. Let's look at our calculator. So on our calculator, I have 1.008 times 2 plus 32.07 plus 4 times 16. That gives me a total mass of 98.086 grams per mole. And it's 1 mole, so I'm going to leave that as grams. That's the mass for 1 mole. Okay, I want to do percent hydrogen in this. That's 2 times the 1.008 grams per mole. This is 2 moles. And that's over the 98.086 grams. And then I multiply that by 100. I'll set up my other two calculations, percent S being 32.07 grams per mole times 1 mole times 100 over 98.086 grams. And then my percent oxygen is going to be 4 mole times 16 grams per mole times 100 divided by 98.086 grams. Whew, that's a lot of calculating. Well, all right, let's go. So 2 times 1.008 times 100 divided by 98.086 is 2.05% hydrogen. So I'm going to write my percent H over here is 2.05%. My percent S I'm going to write here, and my percent O I'm going to write here. So my S, we have that as 32.07 times 1 times 100 divided by 98.086, which gives me 32%. Roughly. And then 4 times 16 times 100 divided by 98.086. And that gives me 65. And if I add all of those happy things together, 2.05 plus 32.70 plus 25.25 at 2.05 plus 32.07 plus 65.25. That's 99.37. I did my math wrong. And again, that's close enough. Since we've done some rounding, that's the reason that it doesn't exactly equal the way that we would expect it to. Awesome possum. So now I've got a percentage for those. Let's see what my next question was. And I'm going to need more paper, so I'm going to get new paper. Let's go back to this. What is the empirical formula for a molecule that is 40.0% carbon? Hydrogen is 6.67%, and oxygen is 53.33%. All right, show me the paper. So I know that these are the percentages that I have. If I assume that I have 100 grams, that means that I have 40 grams of carbon, I have 6.67 grams of hydrogen, and 53.33 grams of oxygen. I know that the molecular weight of carbon is 12.01. Oops, wrong one, sorry. Grams per mole. I know that the hydrogen is 1.008 grams per mole, and the oxygen is 16.00 grams per mole. And we'll pull up our periodic table just to make sure that we didn't screw any of that up. So hydrogen is 1.008. Carbon is over here, 12.01. And oxygen is 16, which is what I wrote down here. So I have that many grams of those things in this. So what was I supposed to do now? Oh yeah, all right. I need to calculate how many moles of each thing that I have. So 40.00 grams of carbon divided by 12.01 grams of carbon per 1 mole of carbon. I also have 6.67 grams of hydrogen. 1 mole of hydrogen is 1.0. Yes, I'm not very good at these things. 1.008 times 2 is 2.016 grams. Hey! And 53.33 grams of oxygen. 1 mole of oxygen is 16 grams. So I should be able to calculate all of those. Awesome possum. So 40 divided by 12.01 is 3.33 and change, 3.331 mole of C. I have 6.67 divided by 2.016. Oh, that's not right. 6.67 divided by 2.016, which gives me 3.31, almost, mole of H. And then I have 53.33 divided by 16, which gives me 3.33 mole of O. So if I write that as C 3.331, H 3.31, O 3.33, and divide by the 3.33, that's going to give me CHO, approximately, as my empirical formula. Ooh, yay, that was fun. Awesome possum. Now, can I do another one? Yes, absolutely. I can do one more. What is the empirical formula for a molecule that has 31.42% S, 31.35% O, and 37.23% F? Now, oxygen is 16 grams per mole. Sulfur, I think, is 32.07. And fluorine, I don't remember. So let's find our periodic table and make sure that the ones we've written down are correct. So fluorine is 19 grams per mole. Oxygen is 16. Sulfur is 32.07. Now let me show you everything that I wrote down. So 31.42% S, which is 32.07 grams per mole. 31.35% O, which is 16 grams per mole, and 37.23% F, which is 19 grams. All right, I want an empirical formula, so I'm assuming that I have 100 grams of total. So 31.42 grams of sulfur at 32.07 grams per mole. I have 31.35 grams of oxygen at 16 grams per mole, and then 37.23 grams of fluorine. 1 mole of F is 19 grams. Let's do some happy math using our calculators. Dun, 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 dun. I'm going to clear this because it bugs me. 31.42 divided by 32.07 is 0.979. 0.979 mole of S. 31.35 divided by 16 is 1.95. 94 mole of O. That's way too many digits. Should be just like that. And then if we do our fluorine, 37.23 divided by 19, that gives me 1.959. So I know it's an S 0.9797, at an O of 1.959, and an F of 1.959. I divide all of this by the 0.9797. That's going to leave me with an S of 1. Sorry. 1.959 divided by 0.9797 is roughly 2. So it's S1O2F2. is the empirical formula that I find for that. Okay? Yahoo! I did all of that. That was fantastic. It's exhausting, but that's fantastic. Okay? Awesome possum. So what's my next question? Well, let's see what's next. Oh, we're asking for questions. Now we're going to talk about determining the empirical formula by experiment. So I take a sample of iron. It's placed in a cubicle and covered with powdered sulfur. The crucible is heated until all the excess sulfur is driven off after the iron reacts with the sulfur. The product weighs 0.522 grams. What is the empirical formula of the iron sulfide complex? Right. So I have a sample. It's 0.331 grams. I know that my product, once I've reacted it, is 0.522 grams. This is iron. It's covered with excess powdered sulfur. That's the product. What is the empirical formula of the iron sulfide? So the mass of the sulfur is equal to the 0.522 grams minus the 0.331 grams, which is 0.191 grams of sulfur. Okay, that means that if I do the calculation to see how many moles of sulfur that I have, I divide by the 32.07 grams per mole, that gives me 0.00596 moles of sulfur. I take the 0.331 grams of iron that I started with, I divide by 55.85 to get the moles of sulfur, and I get 0.00592. If I have that and I reduce that, it reduces to FeS. Okay, so it's the same process that we talked about before, but now instead of assuming what our masses were, we're actually finding data to show us what it was. This is my iron information, and the difference between the product and the iron is the sulfur. Okay, because it's the only thing new that I've introduced. All right. Questions about that? Hopefully not. If you have them, let me know. Let's talk about determining a molecular formula. So far, we've found empirical formulas, which is the lowest whole number ratio between the components in that formula. But how do I know what a molecular formula is going to be for this? How do I know if the empirical formula is actually the molecular formula? That's what we're going to talk about here. So we've only found empirical formulas, which are the lowest whole number ratio of atoms in the molecule. We know that sometimes the formula of a molecule is a multiple of that, like N2O4, which is 2 times NO2. In order to determine a molecular formula, we need to know the approximate molar mass of the compound in addition to finding the empirical formula. So I need enough data to find an empirical formula, and then I need to know what the molar mass is to be able to do a comparison. So if I have 30.46% nitrogen, 69.54% oxygen, and the molar mass is determined to be between 90 and 95, we can do the same thing that we've done before. We assume we have 100 grams, we have 30.46 grams of nitrogen, 69.54 grams of oxygen. We convert both of those to moles, 30.46 grams of nitrogen divided by 1401 grams for nitrogen. That gives me 2.174 moles of nitrogen. 69.54 grams of oxygen divided by 16 grams of oxygen gives me 4.346 moles of oxygen. If I divide both of those by 2.174, that reduces to NO2. So that's my empirical formula, NO2. But the molar mass of NO2, if I take nitrogen, 14.01, plus 32, that gives me 46.01 grams per mole. And that's not consistent with the number that they've given me. Since that's not consistent with that, I need to take this number and divide it by the mass for this empirical formula to see what that ratio is. And if I do that, you'll see that this is 2 times this, which means that I need to take this empirical formula and multiply it by 2 to give me N2O4, and the molar mass is going to be 92.01 grams per mole. So that's consistent with all of the data that we have. So we need to figure out, once we do this, that empirical formula, the mass of that particular thing, what relationship is that between there and the molecular formula they've given you. That relationship will tell you what you need to multiply by to figure out what the molecular formula is. Okay? Here's another example. Let's do it again. Sorry, that came out looking really horrible. So a compound is 75.46% carbon, 4.43% hydrogen, and 20.10% oxygen. Molecular weight is 318.31 grams per mole. What's the molecular formula? We assume 100 grams, so 75.46 grams of carbon, 4.43 grams of hydrogen, and 20.10 grams of oxygen. Convert the 75.46 grams of carbon to moles by dividing by 12. It gives me 6.289 moles of carbon. We take the 4.43 grams of hydrogen, divide it by 1.008, and it gives me 4.39 moles of hydrogen. And even though you can't really see it, 20.10 grams of oxygen divided by 16 grams is then going to give me an answer that I can't really see. Wish I could fix that. No, gee, I could fix that. Give me a second. I know what I'm doing. 20. Turn it back on. 20.10 divided by 16 gives me 1.25625. That should be that number. 1.256 is what I reported there. So 1.256 moles of oxygen, 6.289 moles of carbon, and 4.39 moles of hydrogen. We divide by the smallest number, which is that 1.256. That leaves me with 1 mole of oxygen, 5 moles of carbon, and 3.5 moles of hydrogen. That's not an even number. So if I multiply all of this by 2, I end up with 2 oxygens, 10 carbons, and 7 hydrogens. So C10H7O2. The molar mass of this thing right here is 10 times the 12 plus, so 10 times the carbon, which is 12, plus 7 times 1.008, plus 2 times the 16, which is 159.06 grams per mole. That's not consistent with the 318.31 grams per mole. So we take the 318.31 grams divided by the 159.06, and that gives me 2. So I must multiply the empirical formula by 2 to get the molecular formula, which is then C20H14O4. Yay, that was so exciting. Awesome, sweet. Questions on that? Well, if not, that brings us to the end of this discussion. We've now talked about moles and percent composition. So you should be comfortable calculating the number of moles that you have, calculating a molecular weight, finding an atomic mass, using those things to find the number of particles that you have, to find the ratio for the empirical formulas from the masses and percents that you're given, and then finding empirical or the molecular formulas as well. Those are calculations you should be able to do. Your practice will reflect that, and I will make sure that that practice is available to you fairly quickly. All right, I'm going to stop sharing, and I hope you guys had a great time listening to me, and I will talk to you again soon. Thanks, guys.